OK. Merci d'abord beaucoup pour l'invitation à présenter au séminaire. Je vais pas tenter la présentation en français, tout simplement parce que je pense pas avoir le vocabulaire en français pour le faire correctement. Donc, je vais enchaîner directement en anglais si ça vous dérange pas. So, indeed, I'm going to talk about the developments and capabilities of particle-based methods for microfluidic applications. And so what I'm going to look at in this presentation is high-order multi-component Lattice Boltzmann methods, discussing why we want to use those high-order Lattice Boltzmann approach, the developments that we've been through, and some applications of that. And then I'll move into some coarse graining approaches that we have developed for applications such as liquid marbles and red blood cells, as you can see on the right-hand side, before concluding and giving some perspective of the work that we are doing. Before that, just a brief on QUT. So Michael should remember this campus. So QUT is quite a large university. We've got around 50,000 students. Apparently nearly 13,000 staff members. We're in the top 10 universities within Australia, and we are locating near the CBD of Brisbane in Queensland, so near the Botanic Garden that you can see here along the Brisbane River. So very lovely country, very lovely climate, if you like. Hot and humid summers, that's perfect. And winters are quite mild too, so that's a nice place to be. I just wanted also to give you a brief overview of my background, where I come from. So I basically come from France, of course. I did all my undergrad studies and postgraduate studies in France, mostly in Paris, where I've got my bachelor, my master done in collaboration with the ENSAM. And then I've got a PhD in turbulence modeling with UPMC. From there, I worked nearly 2 years as an external consultant for Peugeot, working on diesel combustion, noise, and injection strategies. And following that, I moved into Western Australia, so the west coast of Australia, into Perth, where I worked in a small engineering company working in oil and gas and mining industries over there. Then I moved to Brisbane, where I initially worked with another engineering company before moving back as a research fellow at the University of Queensland, from where I obtained a fellowship that allowed me to get an ongoing position at QUT, so Queensland University of Technology, and I've been there since 2013. In between, I also spent 4 months at MIT in 2019, just before COVID hit. So I was quite lucky to be able to go there, spending some time in a microfluidic department they are looking at mainly microfluidic applications, but on the experimental side. That's basically my journey since the very beginning. I also want to acknowledge my team, mostly my previous and present PhD students and my postdocs, who have been mostly working on those developments in this computational approach, and also acknowledging the financial support of the Australian Research Council. So a bit of context, let's move on to what we are looking at in my group. And first of all, what I want to look at is different applications, okay? Different scenarios. So we've got some cup of coffees, black coffee, to, you know, how much milk you want in your coffee, to applications of lab-on-a-chip for disease diagnostics, biological assays, any applications in biology and biomedical engineering. On the left-hand side at the bottom, I've got 3D printing applications, especially for polymer flows, looking at scaffolds, for example, again, for biomedical engineering applications. And then on the right-hand side, I've got some ORC applications, looking at renewable energy applications, recovering heat from waste, for example. And so the question is, what do those applications have in common? Because we may think that they're quite diverse applications. And so actually they've got lots of commons. They're all dealing with complex and or non-ideal fluid flows and mixtures. Some of those applications have significant inter and intramolecular interactions where the fluids are not necessarily long in equilibrium. And that raises some complexity in terms of how we want or need or be able to model those interactions. When we look at 3D printing, we also have nonlinearities, statistical fluctuations that leads to some of those instabilities that we can see here in the jetting dynamics of those viscoelastic fluids. Similarly, for organic applications or RC applications, for example, we are looking at mixtures of those non-ideal fluids so that we can try to extract more energy from a given resource. And again, that raised some questions about how do we actually computationally model those fluids and mixtures, looking at those interaction at the molecular level. So moving from that, the problem with those non-ideal fluids is usually there's still some lack of fundamental understanding because of the complexity of their behaviors, of the instabilities that they can create. We don't necessarily have accurate and fast computational models, especially for practical applications. And in my presentation, what we will see is that I'm focusing at the moment on benchmark cases, simplified applications. So again, there are still some steps to be able to look at actual practical applications. The coupling also between those fluids and mixtures and some structural aspects, especially if we look at soft matters, and that's why I've got a section on liquid marbles and red blood cells. But looking at those coupling between complex and non-ideal fluids and soft matters, which is still probably lacking in the literature. And because of all those points before, we also lack some proper engineered design and optimization methodology, especially for microfluidics developments. So all those limit the developments and optimization of microfluidic systems, but not only microfluidic applications, also in the energy technologies or applications such as ORC, for example. So that's why I'm looking at high-order multi-component Lattice Boltzmann approach. And so I'm going to discuss why we are looking at those particular approach. So if I go back to my cup of coffee, what we are interested in understanding is really the interaction at the micro scale. So what's happening at the micro scale that can explain the behavior at the macro scale. And here it's the Kelvin-Helmholtz instabilities that we have observed in the Brisbane sky, basically. But the question is, we've got some similarities in terms of the phenomenon that we can see at the micro scales here that can also translate to the macro scale. But how do we relate those different scales? Of course, we've got some computational techniques that are available at the macro scale. We've got our conventional CFD solvers that are governed by the Navier-Stokes equations that gives us the continuum picture of the fluid flows. That's fine. At the micro scale, we also have some computational techniques, especially molecular dynamics, for example, using the Newton dynamics. And we've got some particle-based solvers that can track individual molecules. Again, those techniques are very expensive computationally, and they don't necessarily, again, they give us some information at the micro scale, but then we can't necessarily relate back to the macro scale phenomena that we want to observe. So there's some intermediate technologies or techniques at the mesoscales that allows us to relate those microscopic parameters to the macroscopic scale. And that's why basically the Lattice Boltzmann comes into play, because we can achieve those this connection between those two different time and length scales. And so that's basically the main motivation for the Lattice Boltzmann, having a bridge between the microscales and the macro scale. In addition to that, we know that the computational power is increasing. We've got better architectures, better materials. We can really do much more in terms of computing and scalability, and that's one of the capabilities of Lattice Boltzmann. So it really has some of those advantages that we can really use for large scale simulations. And when I say large scale simulation in that case, it's really looking at very complex applications where we will have coexistence of physical, chemical, biological phenomena that are very common in bioengineering applications. So just looking at, for example, red blood cell simulations in a coronary tree, that would require heaps of computing power, and hopefully with this increase of computing power and with this technology such as Lattice Boltzmann, then we can really look at much more complicated applications, basically opening new avenues to investigate those applications. Now, in terms of the developments, I'm going to briefly talk about the Lattice Boltzmann itself, but then moving on using high order models, and then including multi-components so that we can look at mixtures, basically. So the Lattice Boltzmann approach, as I said, it's a mesoscopic approach where we have a distribution function f that indicates the density of the particles or the molecules that we are considering in the fluid, and we allocate them with a position, and we give them some discrete velocities and directions at each time t. We then add a statistical probability of the particles that would indicate their interaction with their neighbors' particles. And so we've got this kind of distribution of lattice weights for this statistical probability. From there, we can write an evolution equation that involves the actual distribution function here that has a collision term. So basically, when two particles collide with each other, then they will bounce back from each other with a different velocity and move back to a different location. We can have then an equilibrium forcing terms where we can also include any additional source terms in this term. And then the last is the streaming step. So basically how those particles are going to move from one location to another along those discrete velocity direction that we set with the lattice structure. That's really the basic fundamentals of the Lattice Boltzmann approach. What I'm interested in is the most common or the classical standard lattice structure is what we call a D2Q9. So I'm only focusing on 2 dimensions. So D2 just means that's a 2D case. And then Q9 means that we've got 9 discrete velocities associated with each particles as represented here. The problem is with this particular lattice structure that it's only a second order accurate. And because of that, we can't fully recover the Navier-Stokes equations, which means we won't be able to fully recover the macroscopic behavior of the fluid flow. If we want to be able to further recover the Navier-Stokes equations, we can move to a D2Q17 model, for example, that is represented here. So that's one of the possible lattice structure that we can have. And so with that, it's a third order accuracy, and we can recover the Navier-Stokes equations, but not completely with, we are missing the heat flux, basically. So if we want to fully recover the full thermal Navier-Stokes equations, we need to move to a fourth order accurate lattice structure. And that means at least going into a D2Q49, which means having at least 49 discrete velocities on those lattice structure. So when we look at how those high order lattice structures are obtained, basically there's an equilibrium function in the evolution equation that I've shown before, and that it's obtained or derived by expanding the Maxwell equations by order of Hermite polynomials, and then we project that onto a Gauss quadrature. Now, if we, as I said, if we only look at this second order accurate standard lattice structure, they don't satisfy the Galilean invariance, and they've got a third order scaling error. That means we won't be able to retrieve all the moments of the macroscopic scale. If we increase the order of accuracy to the third and fourth order, then we can have greater isotropy recovered, and then recovering those higher order moments. So what does that mean? That means we will be able to get the physical quantities, the macroscopic physical quantities by doing some summation of the distribution function. And as I said, if we've got a second order accurate lattice Boltzmann approach, we are only capable of retrieving this zeroth and first order moment, that is the density and momentum. If we move to higher order lattice Boltzmann, then we can retrieve the second and third order moments, and so we can retrieve the pressure tensor and we can retrieve the heat flux, meaning that we can fully resolve the Navier-Stokes equation. So that's one of the main reasons why we want to move into higher order lattice structures. So why, again, that's just a summary. Galilean invariance, we can retrieve all the correct momentum dynamics, full Navier-Stokes equations. We can also go beyond the Navier-Stokes equations for Knudsen number, going towards 1 to describe slip and transitional flow. So we can also go beyond this Navier-Stokes level. And then we also have the ability to minimize the spurious velocity because we are recovering higher order isotropic gradients and scalability, as I mentioned before, in terms of parallel capabilities. Now that we've got our high order lattice Boltzmann, we also want to include non-ideal interactions. So as I said, what we want to look at is complex fluids, complex mixtures, and non-ideal mixtures. So what we are doing is we are using the Shenchen pseudopotential that is mimicking the molecular interaction. For that, we've got this force interaction term that involves the self-interaction and cross-interaction, and then we can also add the fluid structure interaction if we've got walls. So basically with that, we've got a relationship dependent on this pseudopotential and on this G term, which is the interaction strength. And then basically we can tune those parameters in the model so that we can tune the interaction at the molecular level. Now, these interactions, as I said, are basically at the microscopic level. So what we want to do then is being able to retrieve the macroscopic quantities such as pressure, surface tension, and diffusion. To do that, we can use the Chapman-Enskog analysis, but we need to be able to retrieve the interaction pressure tensor. And this pressure tensor is going to be dependent on competing interaction at the molecular level. So really this interaction pressure tensor is a key element to retrieve the macroscopic quantities that are interesting in mixtures and in complex fluids. So we've got this relationship that gives us the total momentum flux tensor that has two parts, a kinetic part that we can easily retrieve. So this is not a big problem, but we've got this interaction pressure tensor that we need to be able to calculate. There's two different ways of calculating this parameter. One is a differential approach, one is the exact lattice theory. So what we have is we've got the gradient of the pressure, which is equals to the force term, basically. That's fine. And then from there, we can, at least the literature has demonstrated that there's a standard solution that allows us to retrieve the continuum solution, so the continuum macroscopic pressure tensor. So that's only one of the components of the tensor here that is represented at the continuum level. So we've got this solution, we know that exists. The exact lattice theory, as the name says, is exact. So that's the exact relationship to obtain the pressure tensor at on the lattice itself. And based on that, again, the literature has demonstrated that we can retrieve the pressure at the continuum limit. But the problem is those solutions, those continuum solutions, are dependent on the lattice structure. So each time that we have a different lattice structure, we've got a different solution for this pressure tensor term, which is a bit of a concern if we are moving towards high order lattice structure, because we don't even have those solutions for high order lattice structures. So both of those solutions have problems. The differential approach doesn't have the discrete lattice solution. Okay, so we only have this continuum limit solution of the pressure tensor. The other solution, the exact lattice theory, as I said, it's exact on the lattice structure itself, but the solution at the continuum level is different depending on the lattice structure, which means retrieving the macroscopic properties is becoming complicated. So what we've done is we've developed a general expression that is actually valid for any high order or any lattice structures for this interaction pressure tensor. And what we've done is we demonstrated that the continuum solution is accurate for the macroscopic variables that we want to look at, such as pressure, surface tension, diffusion, and contact angle. So I'm not going to go into the details on how we obtain this development, okay? Just remember that the interaction pressure tensor is related to the interaction force that is given by the Shenchen pseudopotential that I've presented before, and then you can refer to our PRE paper to get all the developments on how we obtain this relationship. The most important is using this discrete solution and using Taylor expansion, we have been able to retrieve the continuum approximation of the pressure tensor, and this expression is true for any lattice structure. That's just an example along the normal components of the x direction for the pressure tensor here. So that's the validation, testing the solution that we have, okay? We are looking at a flat interface where we've got a component on both sides of a different component, the black region, and we look at the center line, the dashed line here. We looked at the pressure, which should be kept constant here, and then the density that is changing with the two different fluid components here. What we see is, with a standard solution at the continuum level, that the purple line here, we've got a big jump at the interface of the solution, which is not what is expected. That should be completely flat. When we look at our continuum approximation and the discrete solution that we have, we basically remain perfectly constant for the pressures through the interface, which is exactly what we wanted to have. What we then did is looking at the mechanical equilibrium condition, which is just the gradient of the pressure being equals to 0. As the pressure is constant, the gradient is 0. And what we see is no matter which lattice structure that we are using, okay, and we've tested a couple of different lattice structure, we then keep this this pressure gradient equals to 0. We've got a small jump here for the standard lattice structure, but when we look at the level of the value itself, it's 10 to the power negative 15, which is basically the machine resolution. So we are not concerned about this slight fluctuation here. So I'm just demonstrating that the solution that we have derived is accurate, and it's valid for any lattice structure that we have tested. From there, now that we have the pressure tensor, then we can calculate the surface tension basically, and that's an example of validating the solution for the surface tension using the Laplace experiment. So now that we can calculate the surface tension with our pressure tensor, we can retrieve the Laplace pressure here. And again, what we've done is we compared again theoretical approximation for many different lattice structures, different order of accuracy and isotropy for those different lattice structure, and all the testing that we have done match perfectly or almost perfectly with the theoretical approximation. So again, validating that our solution is correct. And from there, I'm just going to show you some of the application that we've looked at. Most of them were just tests of what we can achieve with those high-order multi-component lattice Boltzmann approach, just to see if we maintain consistency between those different high-order lattice structures, and if we can get good validation of those models. So now that we've got the pressure tensor and the surface tension, then we can basically calculate the contact angle using the Young's equation. So we can retrieve this theta value. And so what we've done is we looked at a droplet on a solid surface, and we looked at different scenarios where we've got a neutral case, a hydrophobic, and a hydrophilic surface. And we look at this contact angle. Our discrete solution is in red, and we compared again a geometric solution that is obtained from this relationship at the bottom. And we also compared against a droplet shape analysis tool that is used in experiments. And so what we can see that for the neutral case, we actually retrieve perfectly the 90 degrees as expected, and we fit pretty well with this analysis tool that we used. There are some differences with the geometrical approximation that may be due to some resolution of this geometric estimation, basically. Now, when we look at the hydrophobic and hydrophilic cases, we can also see that we are matching pretty well with this analysis tool. There's again a bit more differences with the geometric approximation, but again that gives us a strong confidence that we can retrieve this parameter pretty well from our higher order Lattice Boltzmann approach. Now, with that, what we've done is, again, using this Chapman-Hancock analysis, we have retrieved the full general advection diffusion equation at the continuum limit. And so we've got this diffusion term here that we can establish from this relationship. This is a big step because that then allows us to define different cases in terms of mixtures, where we can define miscible and immiscible cases depending on the diffusion coefficient by setting up this C constant in the model of that we have here. And so again, what we've done is we looked at a miscible case where we've got a sinusoidal decay of a binary mixture, where for which we've got a theoretical solution here, and we compared our models against this theoretical solution. And again, what we can see that we are matching pretty well this analytical solution. So again, that demonstrating that all the developments that we have done so far are giving us pretty accurate results against the theory. And then we went into more exploratory simulations, where we just wanted to see what's going on when we've got those miscible and immiscible mixtures. So we've got a near miscible case here, where we've got two components with two different densities, and what we have at the miscible limit is that those fluids can partially mix, but not completely. And so that's the evolution over time of this process happening. And then when we look at the immiscible mixture, then what we have is over time having those two components completely separating from each other, basically. And so again, in terms of what we were expecting from the model, it's exactly what we were expecting to happen. So we're pretty happy with that. It's purely qualitative visualization. We haven't done any further work in terms of quantifying those different mixtures, basically. And then we also applied the method to non-ideal zeotropic mixtures with realistic fluids. So we looked at R134A and R245FA as a mixture, again, just to look at the capabilities of those high-order multi-component Lattice Boltzmann methods in more realistic configurations. And so what we have is, again, we match pretty well the theoretical prediction. We looked at the worst case scenarios here, looking at gas and liquid. So this case is even more interesting because we've got two different components, so two different fluids, and we also looked at two different phases, so gas and liquid. And so we looked at miscible and immiscible cases where we've got basically the two different components. and the two different phases all together in one simulation. So that basically 4 different components run in the simulation. So R134A as a liquid and a gas, and R245A as a liquid and a gas. And again, that's only possible because we've got the pressure tensor that we have, and that allows us to obtain the diffusion process. And again, as an exploratory investigation, looking at instabilities, we looked at the Rayleigh-Taylor instabilities, and what we wanted to look at is the consistency between 2 different lattice structures, so moving to a different high order, a 3rd order accurate, and a 4th order accurate lattice structure. And again, when we compare, so I've got the anisotropy contour here and the velocity streamline here, the match between the two is pretty good. So we're quite happy to have this consistency between the lattice structure, because again, that means the development that we have made are valid for any lattice structures that we can use or develop. And similarly, we looked at the Kelvin-Helmholtz instability. And again, looking at the comparison between the Q17 and the Q49. So again, a 3rd order and a 4th order accurate simulation. And what we can see that the consistency between those simulations. Again, we can achieve that because we have the transport properties now from our pressure tensor. And again, we only looked at qualitatively of how those 2 fluids are mixing together in the instability. We haven't done any further quantitative analysis of those simulations. So that's the end of the first part of the presentation. Basically, what we have developed and achieved is a high order lattice Boltzmann multi-component model that can simulate complex and non-ideal fluid mixtures. How did we manage to get that? We have a general solution for the interaction pressure tensor that is valid for any lattices. So especially for high order lattices that didn't exist before. And on top of that, we've got the continuum approximation that was derived and from which we can retrieve the macroscopic variables such as diffusion, surface tension, contact angle, as I shown. And again, looking at fluid instabilities, the modeling seems quite robust to those instabilities, and the consistency between those different lattice structure is also giving us confidence that the development that we've made is correct, basically. So now that we've got that, what I want to move into is a different modeling technique. So we are also developing coarse graining approach, in particular for liquid marbles and red blood cells. And of course, ultimately, what we would like to do is merge those 2 different methods together. So coupling the lattice Boltzmann with this coarse graining method, so we can look at, for example, red blood cells in capillaries or in the circulation, basically. So let's start with our coarse grain model for the liquid marbles. So liquid marbles are quite interesting objects that can be used as discrete microfluidic devices for biological assays, drug delivery, but also cell culture and microreactors. They're also used in gas sensing, and basically what they are a liquid droplet that is coated with some superhydrophobic powder. And because of that, they've got quite interesting characteristics, and they can be characterized using elastic solid models, for example. So in that case, what we have done is currently we've got a 2D model of those liquid marbles. And so what we've done is just take a cross-section of this droplet or marble, and we have defined 2 layers of particles, an inside layer of particles to represent the inside liquid, assuming that is incompressible. And then we've got the external layer of particles to represent the coating. What we have is including pressure due to surface tension, the hydrostatic pressure, and we are using Lennard-Jones forces to model the interactions between the particles, so between the liquid and the solid particles, and between solid and solid particles around this layer of coating, basically. And so what we've done is we looked at the applicability of this model, validating for a water droplet coated with nanoparticles. And so there are some experiments where they looked at different size of marbles, and depending on the size of the marbles, basically when you put those on a flat surface, the bigger they are, the larger puddle shape like they take. And so we validated against some measurements of the height and the width of these marbles when they are sitting on a surface. And what you can see that the comparison against the experiments is pretty good. What we also looked at, and again, that was more of exploratory investigation. As I said, those marbles can be used for drug delivery, for example. And what happens is they put some magnetic particles for the coating and putting a magnet at the bottom, for example, to make sure that these marbles or the coating can open to deliver what's inside, basically. And so we just wanted to see if we could reproduce this kind of things. And so what we have in the initial stage is putting the marble on the flat surface, getting this puddle shape. And then at the bottom, we've got a magnetic field applied to those external particles. And so basically what happens is that the attraction from this magnetic force is allowing those external particles to move towards the magnet and open the top surface of the coating, basically. What we haven't done is then removing the magnet to see if we can get back to the closure of the marble, because in experiments that's what they have. They put the magnet, open the marble, and then remove the magnet so the marble can close back, basically. But it's a pretty nice application that we can look at with those coarse grain techniques, basically. And then the last thing that we've looked at is the compression of a liquid marble. So we put the marble between two plates and compressed this marble, and we compared. We looked at different size of marbles, different fluid densities, different aspects of that. And we are collaborating with some colleagues at Griffith University in Brisbane who are doing all those experiments. And so what we ended up establishing is a non-dimensional relationship between the stress and the strain of those liquid marbles when we compress them. So that the validation basically of this non-dimensional relationship that we've obtained against the experimental points over there. So we've got this relationship here. And of course, there are probably many more things that we could do with those liquid marbles. One thing would be to look at coalescence of two liquid marbles that can be that has been experimentally done for reaction, for example. So you've got one component in one marble, another component in another one, and then you make them connected to each other so that you can control the reaction between those two components, for example. So that's something that we could look at in the future. And so a big other aspect of what we're doing in my group is red blood cell modeling. And so red blood cells are soft matters that takes many different morphologies, as you can see in this slide, from stomatocyte to discocyte to iconocyte. That's the spiky shape here. And there has been some previous computational models that look at those morphologies. The main difference with our model is we are capable of obtaining all the morphologies, so even the spherostomatocyte and the spheroechinocyte shapes. So we can not only limit ourselves to this echinocyte 3 or stomatocyte 3, but we can go all the way through the morphologies that can be observed for those red blood cells. I'm not going to go into the details of the computational method, but basically it's an energy-based approach based on coarse graining, and it's an energy minimization problem that we are solving, basically representing the membrane of the red blood cells by a number of particles that are connected, and setting up some mechanical characteristics of the interaction between the particles, such as bending stiffness. We also set the surface area ratio of the red blood cells, the total volume of the red blood cell, etc., that we can then control, basically, to obtain those different morphologies. And so what we've done is we did some comparison against some experimental visualizations that have been done in our group, and we tried to quantify the difference between our model and this experimental observation. So we used the confocal microscopy imaging. We then retrieved the shape using a triangulated surface mesh, and then we compared those to this experimentally reshaped one against our computational model. Overall, there are some differences for the different parameters that we looked at, with the highest difference is around 20%. But again, based on the complexity of the shape, I'm not surprised to have 20% difference, but I think that's already a pretty good achievement for those type of modeling. What we also did is we compared, so there are some published work on stretching those red blood cells. This stretching is done purely on the discocyte shape, and so what we've done is comparing the stretching for our model, so the red one, against the experimental stretching here. And so with those large standard deviation from the experiments, we're almost within the standard deviation of the experiment, so we're pretty happy also with that. The other good point is that we can also stretch all the other morphologies, and so we can clearly see that depending on the morphologies, the level of force that you need to stretch those different shapes is different, and that can be used basically to evaluate their deformability. That is important as a characteristic for filtration by the spleen, for example. So that's one of the characteristics that is used. And then what we've done is we tried starting coupling those red blood cell models and putting them into a flow, capillary flow. What we are using at the moment is a coupled coarse grain SPH approach, because we had some previous students working on SPH, but again, the following step would be transferring or swapping the SPH for a Lattice Boltzmann, just because the SPH approach is very computationally intense. And so we hope that using Lattice Boltzmann, the efficiency of the simulation would be much faster. And so what we have again is all the different morphologies that we can think of, flowing them on a straight microchannel. And so what we see is that no matter of the shape of the morphology of the red blood cell, they all take this parachute-like shape after a while. Okay. Oops, sorry. And of course, ultimately, what we would like to do is putting many different morphologies all together in a flow, so that we can add more into the physics in terms of how those different cells will interact with each other, but also with the walls. We may have to add electric charges on those red blood cells to make them more complex when they interact with walls. And again, what we have also looked at is, if I move back maybe here, what we've looked at with those morphologies is how do we retrieve different morphologies back. So we know that those echinocytes up to the third stage can be move back to their discocyte shape, for example, if we use different solutions. And that's what the numerical model has shown, that if we can change their environment, those morphologies can retrieve their original shape, basically. And that's important in terms of storage of red blood cells, because we want to make sure that they're in their base shape before transfusion, and they're are as healthy as possible before transfusion. We've also shown numerically that those stage 4 can't go back to their discocyte shape, no matter what we try to do with them. So that's basically the capabilities of the current model that we have. The end of my talk for today. So as I said, we now have a high order multi-component lattice Boltzmann method that is capable of simulating accurately complex and non-ideal fluid flows and mixtures. And we've got these coarse grain models that can look at liquid marbles, but also deformation and deformability of different red blood cell morphologies that we can look at. That's, as I said, along the way, that's not the end of the journey. We've got still many things to look at. All the benchmark cases that I've presented for the high order multi-component lattice Boltzmann are usually very simple in terms of the boundary conditions that we are using. Most of them are periodic boundary conditions. And so one thing to do is looking at more realistic boundary conditions so that we can also move into practical applications. We will have to move into 3 dimensions, of course, and also put the code into GPU so that we can make the simulations much faster. As I said before, coupling the two, so the lattice Boltzmann approach with the red blood cell membrane model would be also an interesting step for us. And the other thing is to look at viscoelastic models. So how do we incorporate viscoelastic models into those high-order multi-component lattice Boltzmann approach, so that we can look at mixing of viscoelastic fluids, which are quite an important topic for microfluidics. Just because mixing is complicated at the microscale, especially at Reynolds number around 1, where there's nothing much than diffusion to allow for mixing easily. So unless we move into active mixing technologies, there are some ideas around using elastic turbulence as a regime that can trigger instabilities and can allow for improvements in mixing at the microscale, basically. So that's a very interesting regime that surely shows some chaotic regime and instabilities that are due to elastic and combination of viscous and elastic stresses in a flow where inertia is almost completely absent. So really looking at very low Reynolds number, where inertia is not playing a role, but we can still see some behaviors that are comparable to turbulence. And that's why it's called elastic turbulence, because it's not inertial turbulence, basically, to make the difference. But again, that's some preliminary simulation that we have done on a 4-roll mill benchmark case, where we are basically stretching some polymer. So the red region here is the polymer stress that we are stretching. And what we can see that after a while, you've got instabilities occurring. And when we look at the vorticity on this right-hand side, we've got 4 quadrants appearing, and they are basically rotating across the 4 quadrants of the geometry. But those very chaotic regime, again, ends up being in the elastic turbulence regime, and using those high-order multi-component models coupled with the viscoelastic model, allows us to investigate those kind of applications, and hopefully that could give us some indication or better understanding of the mechanism to improve mixing at the micro scale, basically. And that's the end of my presentation. Thanks a lot for listening, and I'm happy to receive any questions that you may have.
Merci beaucoup, Emilie. Ouais. Merci beaucoup pour cette très belle présentation.